Hello, everyone. Welcome to Chapter 8 review for AP Statistics. This chapter was all about confidence intervals. So that's what we were going to be getting into. We're going to tie stuff from previous chapters into our new unit. And this one is going to include three sections. The first one is just an introduction to confidence intervals, just in general. Then we have a confidence intervals for proportions, and then we have confidence intervals for means. We look at those two separately because there's a few differences between them. So let's get started. First of all, just a general introduction. Before we talk about confidence intervals, though, let's talk about why we need them. In previous chapters, we looked at a sampling distribution, and we know that the mean of the sampling distribution is going to be equal to the population mean. We're talking about means right now, because sampling distributions are for means. For proportions, we have the yes-no charts. But we have this sampling distribution, and we can say that the mean of the sampling distribution is the mean of the population distribution. However, what if you only have one sample? Because the sampling distribution is made up of all possible samples there are. But in reality, all you can do is take one sample, maybe a few more if you want to really test things out. But you can't take all possible samples, especially when it's a big thing. So what you're going to do is use a confidence interval to estimate where the population parameter is given your statistic that you found through the sample. So the point estimator is going to be the variable. So it's either going to be x bar or p hat. X bar, as we know, is for means, and p hat is for proportions. And their population counterparts is mu for means and just p for populations. Now, if in a given problem, we have a point estimator that has a value of the point estimate. The point estimate is the given value. So if you know that x bar is 18.5 in a given problem, the point estimator is x bar, and the point estimate is 18.5. Now that we got that basic terminology out of the way, let's talk about confidence intervals, the entire point of this unit. So the confidence interval is going to be a range, basically, where the point estimate or the statistic you're using is going to be at the center of it, and it has some leeway where the actual parameter of the entire population can be. Now, there are different types of confidence intervals, and we'll get to that on the next slide. But first, here's a diagram to basically recap everything we know about sampling distributions and population distributions so far. If we have a population, we know the mean, mu, is going to be a certain value, and that is what we learned up till a few chapters ago. And then in chapter 7, we talked about sampling distributions and how we don't know the population distribution. Instead, we use sampling distributions to estimate that. Now, why does this work? We know that the mean of the sampling distribution is going to be the mean of the population. However, as I mentioned before, we're not given all possible samples. We're only given one. So while this method works in previous chapters, now we are dealing with reality where we only have one sample. So we have to use a confidence interval to estimate the population parameter. Okay, we're given a C% confidence interval. C is going to be any number, usually going to be above 90 to have a pretty confident interval. And the most common one is probably 95 or 99 or something like that. 95 is pretty important because according to the 68, 95, 99.7 rule, it's almost exactly 2 standard deviations. It's a bit less, and we'll talk about that in a while. But it's almost exactly 2 standard deviations away. And that is pretty useful. So we'll get to the 2 a bit later, once we have a specific formula for a C% confidence interval. Right now, all we can say is it's going to be the point estimate, which I'm going to abbreviate with PE, plus or minus the margin of error, which I'm going to abbreviate with ME. So the point estimate plus or minus the margin of error. And the margin of error is just going to be how much above and below the range makes up. So like I said, margin of error, or ME, is going to be equal to the maximum possible value in the interval minus the mean of the interval, or the point estimate, or it's also the point estimate minus the minimum value of the interval. And the confidence level is what C is. And like I said, it could be 95, it could be 80, it could even be 68 if you wanted. But trust me, I don't think you want a 68% confidence interval because you're not going to be very confident about that. The thing with confidence in levels is the lower you are, the smaller your interval is. And I'll show you a diagram in a minute. But basically, you kind of want a tight interval so you can say this is how confident I am, and look at how small of an interval it is. You basically can say that the parameter is going to be in this very small interval, so it's pretty accurate. However, your confidence level is also very low at that point. 68% confidence interval means approximately 1 standard deviation away. And while that is pretty small, 68% is also not very confident at all. Instead, what we want is a 95% confidence interval. And sometimes that's pretty big, but that's still 95% confidence, which is pretty impressive. So it's that balance between how much confidence you want and how small you want the interval. Now we finally get to interpreting confidence intervals. So if we're given a confidence interval, let's have an example of a 95% confidence interval, usually abbreviated with the CI for confidence interval. What does that mean exactly? So there's a standard phrase you should always say. We are C% confidence that the interval from blank to blank captures the blank. Okay, that's a lot of blanks and variables. So the C, as you might imagine, is going to be equal to whatever that confidence level is. So we are 95% confident that the interval from, and that's going to be the lower bound of the interval to the upper bound of the interval. So let's use our old example of x bar equals 18.5. And let's assume that the standard deviation is 1, which means 95% is approximately 2 standard deviations. We can use that approximation for now. So 2 below, 2 above. So it's going to be from 16.5 to 20.5. Captures the what? Well, what are you trying to measure? The population mean, and you're usually given context for a problem. So what you want to say is the mean weight of a gummy bear, for instance, if that's the context of the problem. And you usually want to write true before that, captures the true mean or the actual mean to show that it's the mean of the population and not the mean of the sample. Now, I do agree that we're talking about means right now, but we can also talk about proportions. This is just a general introduction, so I'm using a random example involving means. We'll get to proportions in a few minutes. Moving on, there's another thing we can interpret, and that's the confidence levels. So we say we're 95% confident, but what does that mean? If we take many samples of the same size from this population, about C% of them will result in an interval that captures the actual parameter value. Okay, that's pretty long, so let's break it down. If we take many samples of the same size from this population, okay, pause. We know the size of the sample. The sample size is n usually, and we usually know it in the problem. If we take many of those samples, basically, if we started building a sampling distribution, about C% of them, so C is the confidence level, so about 95% of them, will result in an interval that captures the actual parameter value. What this basically says is, in the long run, I have so many samples. So think back to probability where we go, in the long run, if I roll the dice 1,000 times, it'll roll an even number 500 times approximately. So that basically says 50% in the long run. But if you roll 2, not necessarily 1 is an even number and 1 is an odd number. It could be both even, it could be both odd. It's talking about in the long run. So same with this one. In the long run, about 95% or C% in general will have an interval that captures the actual parameter value. So let me show you a diagram that demonstrates this. Here, we took a bunch of sample sizes, and they're all the same size, and we constructed the confidence intervals of them. So that's the sampling distribution using all samples, and the mean of that is also the population mean. So we want that mean, mu, right there, to be in the interval that we draw. So let's take the first one, for example. This is going to be the sample mean. And if we're this overseeing God, we know that it's actually pretty close to the population mean. We're pretty good with that estimate. But since in most problems we don't know the actual population mean, we can't say that for sure. All we know is that that's the sample mean, this is the confidence interval. And we're 95% confident that the population mean is in this interval. Now, I'm going to talk about this a bit more, but that doesn't mean that this probability is 95%. Sounds very confusing, but I promise I'll get to it later. However, in this set, one interval completely misses the population mean. So the sample mean is all the way out here, which is very possible, not plausible, but it is possible. And the confidence interval is reaching out till here, which does not go to the population mean itself, which means that this misses the true mu, and we have no way of knowing that. All we know is that we're 95% confident that an interval of this size captures it. We don't know about this specific one. And this also illustrates something else. I said in the long run, remember? Which means that if we only take the first one, that doesn't mean that it's almost guaranteed to capture it, because 95% is close to 100%. In fact, if we only take this interval, that doesn't mean that it's almost guaranteed to capture it. In fact, we know that it doesn't capture it. So all it means is in the long run, after we take so many of them, approximately 95% of them will capture. All right, now moving on. Some more stuff. So there's a general formula for confidence interval. I talked to you about the point estimate plus or minus the margin of error. Yeah, that's a general formula, but let's get a bit more specific. It's also equal to the point estimate plus or minus the critical value. And these abbreviations I'm using are not the official ones. You shouldn't use these abbreviations. You should actually write out critical value and point estimate. For margin of error, you can write ME, but for the others, you shouldn't. I'm only doing it because it'll take too long to write the entire word multiple times. But it's something called the critical value times the standard deviation, and that I can abbreviate as SD. Or it can also be sigma. Mu is the mean, sigma is the standard deviation. Okay, this is the standard deviation of the population. So let's say we know that the point estimate is 18.5, like we used a couple of times before. And the standard deviation of the population, not of the sample, of the population is 1.2. Now, the critical value, what is that? So that is basically the value that represents the confidence level. A C% confidence level corresponds to a critical value of CV, right? Let's put that in numbers. A 95% confidence interval, a confidence level, corresponds to approximately 2. Remember, approximately. It's actually 1.96, but we can use 2 for this section. Once we get into further sections, we're going to have to use 1.96. But 2 is going to be the critical value in this case. 2 times the standard deviation is 2.4. And now you do 18.5 plus or minus 2.4. In a previous example, I said the standard deviation was 1 and 95% correlates to 2. So this time I'm using 1.2 instead of 1 just because you're probably never going to have a standard deviation of 1 that is just too simple. But it's basically the same idea. Back then, I didn't tell you that it's the critical value times the standard deviation. I just told you the margin of error is 2 times the standard deviation, but I didn't tell you about the critical value. In fact, that's what we're going to be talking about later, how to find the critical value for proportions and means. But first, before we get into those sections, a few cautionary statements. One of them is what I mentioned before, the probability that a certain confidence interval captures the population mean. It's not C%. You might be thinking, what in the world am I talking about? Obviously, that's the entire point of the confidence interval. It's 95% confident. Yes, it's 95% confident. That doesn't mean that the probability is 95%. In the long run, the probability, about 95% of them capture the population mean. However, once you create a confidence interval, the probability is no longer 95% because it's already created. For instance, if you already flip a coin and close your eyes so you don't see the result, that doesn't mean that the probability is 50%. It means it's either 100% or it's 0%, because the event already happened. And if you then look at it, then you know for sure, oh yes, it's a head, so 100%. Oh no, it's a tail, so 0%. Without looking at it though, it's either 0 or 100, it's not 50. So in this case, if you have a 95% confidence interval that you built already, the probability that it captures the population mean isn't 95%. It either captures it or it doesn't. So it's either 100 or 0 once it's already built. So that's just one thing to know. There's probably going to be a question like that, so be careful. Another thing is that the calculation assumes that the data comes from a simple random sample of size n. No cluster samples, no stratified samples, a simple random sample. So all of these, the standard deviation times the critical value and the point estimate and everything, that entire formula comes from a simple random sample. Be careful of that. And the margin of error, the word itself says margin of error. Errors, biases should be included. It only includes chance variation. It only includes bias due to random sampling. So actually, it doesn't include bias. It only includes chance variation. So there's a difference. Chance variation is something we don't have any control over. Bias is non-response bias. It's wording of question bias, for instance. Those biases are not included in here because they can be controlled, or they're not due to the random sample itself. So if a question asks you what error does the margin of error represent, just say chance variation due to random sampling, because that's all it is, nothing else, no biases. It's time for an example problem. So this example is from the class. All the examples I use here are from the either the textbook or the actual AP exam that we covered, but I'm gonna solve it here again for an example. So this problem says a large company is concerned that many of its employees are in poor physical condition, which can result in decreased productivity. To determine how many steps each employee takes per day, on average, the company provides a pedometer to 50 randomly selected employees to use for one 24-hour period. After collecting the data, the company statistician reports a 95% confidence interval of 4547 steps to 8473 steps. All right, that was a long problem, but let's break it down a bit. What's the sample? It's 50 randomly selected employees. Randomly selected, key problem. One 24-hour period, that's not very important. It's a 95% confidence interval, and this is the lower bound, that's the upper bound. Okay, interpret the confidence interval. We know how to do that. We are 95% confident, because that's the confidence interval, that the interval from the lower bound, which is 4547, to 8473, captures what? What is the population mean measuring? It is the actual mean number of steps that an employee takes. So this is basically all you need to write for part A. And of course, before I explain this problem, you feel free to pause it, write down an answer, and compare with my answer, so that you can try to learn for yourself. And don't worry if you didn't get it on the first try, because there's this specific format you need to follow. We covered it before, but this in practice is basically what you would write. Okay, so that's for part A. Part B says, what is the point estimate that was used to create the interval? What is the margin of error? So if we already know the interval, we're basically working backwards to find the point estimate. We know that the point estimate is in the center, and then it's plus the margin of error to go up here and minus the margin of error to go down there. So if you were to find the midpoint of this interval, feel free to pause and do it yourself. It's just a simple calculator problem. You add the two numbers, divide by 2 to find exactly the middle of that, and you're going to get 6510 steps. And now you have to find the margin of error. It also asks for that. So be careful of problems that ask for two things. Always answer both of them. Now you just do the maximum number minus the point estimate, and you're going to get the margin of error. You can also do the point estimate minus the smallest number. You'll still get the same margin of error. In this case, you do 8473 minus 6510, plug into your calculator, you're going to get 1963. So the margin of error is 1963. The point estimate is 6510 steps. Okay, I'm going to clear the board since we are running out of space to do part C, but that's basically how you solve this kind of problem. For part C, okay, recent guidelines suggest that people aim for 10,000 steps per day. Is there convincing evidence that the employees of this company are not meeting the guideline on average? Explain. So we know the interval is from 4547 to 8473. Now this is an example of a problem that we did not learn how to do yet. So that's why I'm using this example to teach you how to do. All of these numbers are less than 10,000, which means that we are 95% confident that 10,000 isn't in here, basically. So there is convincing evidence that the employees are not meeting the guideline. So what you would just say is because 10,000 is not included in this interval, and one teachable moment here is 10,000 can be absolutely anywhere in this interval. For example, if the interval is from 4,547 to 10,000, there is not convincing evidence. But if it's 4,547 to 9,999, there is convincing evidence that they're not meeting this guideline. It's kind of arbitrary, but just note that if 10,000 appears anywhere in the interval, it is a very plausible value for the population. So what we say is because 10,000 is not included in the interval, there is convincing evidence, or there is evidence that the employees of this company, and be sure to write of this company because we're defining that the population is the employees of this company, are not meeting the guideline. Now, on the other hand, if the interval was from 14,547 to 18,473, you can say they are meeting the guideline, or there isn't convincing evidence that they're not meeting the guideline because all the numbers are above 10,000. So you can rephrase this to make it more clear. Because all of the values in the interval are less than 10,000, there is convincing evidence. And that would probably make it more clear because even from 14,547 to 18,473, 10,000 is not included, but there is not convincing evidence. So if you want to avoid ambiguity, you should probably rewrite it down. All right, that's it for this example. Moving on to our next section, confidence intervals for proportions. All right, we talked about just general basics of confidence intervals. Now comes the hard part. We get into some confusing parts, so I'll try my best to explain it as best as I can. So before you solve any problem, you have to check the conditions. There are three main conditions for proportions, and these are also the same conditions for means. The third one is slightly different for means, so be careful of that, but the names of the conditions at least are the same. First is the random condition. You need to make sure that it was a simple random sample that got the values or got the statistics. The 10% condition is something we've worked with before. We know that the sample size n cannot be greater than 1/10 of the entire population size. So I'm just going to write population size as a big P, not to be confused with P the proportion. Basically saying n has to be less than or equal to 10% of the entire population size. And the next condition is called the large counts condition, but we can also call it the normal condition. I would generally, honestly, it should be fine to use both, but if you want to avoid ambiguity, you should probably call it the large counts condition. So what this condition says, again, we worked with this before for proportions, remember? So what this says is that the number of successes has to be at least 10 and the number of failures has to be at least 10. So a success in the proportions is the number of the size, basically, times the p-value has to be greater than or equal to 10, and n times 1 minus p hat also has to be greater than or equal to 10. There has to be at least 10 successes and 10 failures in the sample. If all three of these conditions are met, you can move forward. And most likely all three of them will be met because they're not going to just have you not do the problem because these conditions are met. Even though you're probably going to have a problem that has all the conditions met, you still have to check the conditions anyway. It's just good practice too. Okay, now what's the formula for confidence intervals of proportions? We talked about the general formula, but it's a bit different for proportions. So we still have the point estimate. However, in this example, it's going to be a proportion. We know that because it's confidence intervals for proportions. And the point estimate, or the statistic for proportions, is p hat. So we can replace it with that. Plus or minus the critical value times the standard deviation. Critical value, I'm going to leave it like that for now. Standard deviation, I'm going to change to what we know. We know that the formula for the standard deviation of a proportion is going to be square root of p hat, or sorry, p times 1 minus p over n. Basically, the population proportion times 1 minus the population proportion. So basically, the probability of success times the probability of failure over n, and you take the square root of that. The only problem here is, and I kind of gave it away a bit before, we don't know p. The entire point of finding the confidence interval is that we only know p hat, and we want to estimate p. So why would we use a formula that has p in it? Instead, we use p hat, and p hat is close enough to p, generally, that we can assume that this is close enough. Therefore, we have to use something called z star, or the critical value z star, instead of c. So I'm going to rewrite this entire thing to make it look better. Z star is this value that you get that relates to the confidence level, and it's going to be 1.96 for 95%. We already found that out. So remember, it should be p in this formula, but it's p hat because we don't know p. So it's an estimate. That's why z star exists. Okay, let's talk about a bit more about z star. The two parts are standard error and the critical value z star. I'm going to talk about z star first because I just said I was going to do that. Z star is basically a number like the critical value we did in previous problems that estimates the value for the confidence level. The standard error is basically what you just saw before. It's only the standard deviation. However, we call it the standard error because, like I said, we're estimating the standard deviation using p hat. It's not the actual standard deviation, so we cannot call it the standard deviation. We have to call it the standard error because it's an estimate of the standard deviation. And the confidence interval that we get using this is called the one sample z interval for population proportion. Pretty long, but it's also pretty necessary. So how do we find z star? There's a few ways we can do it. First of all, if you use table A, you can find the actual area under. So let's say we know that the confidence interval is, or confidence level is 0.9 or 90%. We don't know the critical value for that off the top of our head. So we have a few options. First one, like I said, table A, you go to 0.9 as the area, and you're going to get a value, an approximate value for z star. However, it's not very accurate because it's unlikely that the area you're looking for is exactly the confidence level. So there might be 0.93. I'm just making up random numbers because I don't know exactly what's in table A. But there might be something close, so you can use it to estimate, but that's generally not the preferred way. Another way is table B. And table B is actually something we're going to use later on in this unit with means. But table B, ignore the DF in table B. That's called degrees of freedom, and we'll get to that later. But table B, if you look at the bottommost column or bottommost row in table B, it's going to be a set of percentages, 90%, 95%, and so on. And these are the most common confidence levels you'll need. And the row above that has infinity next to it. Ignore that. And look at those values. Those are the Z star values for the corresponding critical value, for the corresponding confidence level. Okay, but what if table B doesn't have the one you're looking for? What if it's something like 0.873 and you're not going to get something like that, trust me. But you don't know how to find it? Well, there is a key feature on your calculator that you can use. Go to inverse norm, and it's going to ask you for an area. Now, let's use 0.9 as an example because it's easier to work with. I just use this because I was introducing stuff that aren't in the table. If you enter 0.9 as the area, and area from the left, and you have a mu of 0 and a sigma of 1, because we're talking about standardized normal curve. So it's always going to be a mean of 0 and a standard deviation of 1. So if you enter that in, you're going to get 1.28, which is not what we're looking for. I know. But there's a reason for that, and that's something you should absolutely internalize. If you're looking at a standardized normal curve like this, pretty bad normal curve, but just use this for an example. We want the 90% that is within the mean. So it's going to look something like that. What inverse norm thinks you mean is from the left. So all the way to infinity to this, what area is 90%? That's not what we want. Some calculators have a feature, center, that if you do 0.9 and center, you're going to get the correct value. However, other calculators don't, and this foolproof way to do it, you actually have two ways. First of all, if this is 0.9, you can find out what the lower bound is. So 0.9, that means 0.1 is on the ends. 0.9 is in the middle, so the remaining, which is 0.1, is on the ends. You take half of that, 0.05 on each end. And you can do inverse norm of 0.05, and that's going to give you negative 1.645. You just remove the negative sign, and that's your Z star value. Because this is actually the negative version of this one. It's the same as that, but negative because it's on the other side of the mean. So if you remove the negative value, you're done. Or you can do 0.9, the area, plus this extra area at the beginning to get this value. You got the extra at the beginning, plus everything in the center that you need, and then you got the final value. So 0.9 plus 0.05, or basically 0.95, and you're going to get the exact same answer as you did with 0.05, but positive. That's going to be the Z star. Either way you choose, or you can even do center if that's an option for you, but if you're not, there's another way you can do it. So that's how you find Z star. And now to actually find the one sample Z interval for population proportion. Okay, the formula for this is, like we said, P hat plus or minus Z star times the square root of P hat times 1 minus P hat over N. That's going to be your equation. And now we basically know everything. We know P hat, which covers all this. We know N, and we know Z star. We can start solving problems. There's one more thing you should know, and that's actually a function on your calculator. So if you go to not the same place where you find norm CDF and inverse norm, but if you go to confidence intervals, there's something called one prop Z interval. That's what we want to use. Not just Z interval, not two sample Z interval, and not two prop Z interval, but one prop, because there's only one population that we're looking at, one prop, so we're only looking at proportions, and Z interval. So if you use that, it's going to ask you for your proportion of success. So we're going to come to an example with that later. So let's just say 0.65 for an example. N is 50, let's say we have a population of a sample size of 50, and the sea level is 0.95. Now, in this case, you don't really need to you don't need to add the extra little bit at the front for the confidence level, because it's just asking for the confidence level and not the area. Okay. So this is basically how you write the solution for an example. And I'm going to go through an example written this way as a proper solution for these kind of problems. If you think back to previous chapters, we use this 4-step process called the state, plan, do, conclude process. So first off, we want to state something. What we want to state is what we're looking for. We want to estimate P. That's going to be the population proportion or the parameter. And we have to describe it using the context we're given. We want to estimate P, the total proportion of coffee drinkers in the US. If conditions are met, okay, now we're moving on to the second step. State plan. We're planning to create, we need to include the confidence level we need and exactly what type of interval it is. It's a one sample Z interval, like I said before. That's what it's called. You have to write that. So this is the plan part, but there's one more bit to the plan part, and that's to actually check the conditions. We just said if conditions are met, meaning we need to actually check the conditions to make sure they're met. First off, we have the random condition, we have the 10% condition, and we have the large counts and normal condition. So you actually have to check them. You have to say, oh yeah, this is a random sample. The entire population is more than 10 times this, blah, blah, blah. And I'll show you an example where we do all of this. Then you do the actual calculations. You should generally do the calculations, even if you use the calculator, you use 1PROB-Z interval, you should write down your work you write the formula, you plug in values, and then you get the answer. That's because if you don't and you get it wrong, you're not going to get any points. If you do write down the work and get it wrong, you'll get some points for actually knowing what it is, what is one sample Z interval and the formula and everything. And then finally, you interpret the confidence interval like we've done before. And that's basically it. And then you answer any other questions if there are. So, time for an example. During a flu vaccine shortage, blah, blah, blah. I'm not going to read this entire one. I did for the previous one because it was our first example, but feel free to pause, read it, solve it, and I'll just start by highlighting the important stuff. So 45%, that is unnecessary information for now. We do need to comment on it later, but for now, that's going to be the population proportion of a previous study or of a belief, basically, or someone said this. We want to make sure that it's true. So we take a sample or a random sample of 2,350 vaccine eligible people, and 978 of these people received the flu vaccine. So real quick, I'm going to, first off, everything you need to do, you need to calculate what that proportion is. You're going to find out it's 0.416. Okay. That's nice to know. Now, let's actually write the solution like we should. This is saying constructed 99% confidence interval for the proportion, and we'll get to the second part later. It says use your confidence interval to comment on the belief that 45% of the vaccine eligible people. Okay. Let's actually write it down though. First of all, we want to estimate P, the proportion of vaccine eligible people who had received the flu vaccine. That's the entire context. And then we move on to the plan part. If conditions are met, we will construct a 99%, that's the confidence level, one sample Z interval for P. Good. Now we actually have to check the conditions. The random condition, I even highlighted this. It says that it was a random sample. So that means this condition was met. Then the 10% condition. So we know that it was 2,350 people in the sample. 10 times that is 23,500. And we can safely assume that there are at least 23,500 vaccine eligible people in the US. So that's met. We know the population definitely is more than this. And finally, the large counts or normal condition, we know that 978 successes, so that's greater than or equal to 10. And we know that 2,350 minus 978 is greater than or equal to 10. We don't really have to solve for it right now. We could, obviously, but we don't have to. But we do definitely know that it's greater than or equal to 10. So this is also success. All the conditions are met. We can move on to the next phase, which is do. State plan do. We actually do the calculations now. And I'm going to show you on the screen what you should write. The formula, so p hat is the point estimate plus or minus z star times the square root of p hat times 1 minus p hat over n. This is the standard error, remember. And this is our formula. So then we plug in values. We know the proportion is 0.416, and you can go beyond that, 4162 approximately, plus or minus z star. Okay, how do we find this? We go to inverse norm. You plug in the area. So it's 99%, so the area is going to be 99. Remaining is 1% split on each side. So it's going to be 1 divided by 2, or 99.5. So it's going to be a 99.5 area, or basically 0.995 is the area. This is assuming you don't have table B. Table B definitely has a confidence level of 99 on there, so you can check that if you want as well. But assuming you don't, it's going to be 2.576. 576 is going to be your z star times the square root of p hat, we know is 0.4162, times 1 minus the p hat. So you know p hat is 0.4162. So 1 minus that is 0.5838. And all this over the sample size, we know that to be 2350. And now you calculate for this, or you can use your button on your calculator, which I am actually going to do. You go to 1 prob z interval. The number of successes is 978. N is 2350. And confidence level, we want 0.99, not 0.95. You plug it in, and you get the lower interval is 0.389, approximately 3899. It actually rounds to 3900, but I'm going to write 3899 because 3900 isn't very, it doesn't seem very accurate, at least. And then 0.4424 is the upper. So that's going to be your interval. You did the do part, you got your answer. Now we need to conclude. How do we conclude? We interpret it. And I'm going to erase this since it's interfering with other text. So we're 99% confident that the interval from 0.3899 to 0.4474 captures the true proportion of, and then use the context, vaccine eligible people who had received the flu vaccine. Now there was one more part to this problem. It said that 45% were, it was believed that 45% received the flu vaccine. However, 45% is more than this. So all of these numbers are less than 45. 45 doesn't appear anywhere in this interval, meaning it doesn't support the conclusion. 45% is not in the interval, so the evidence does not support this claim. That's all you have to write for that. So this upper part, starting with we want, is going to be part A, and the bottom part is going to be part B, where we talk about 45%. Okay, there's one more thing we have to talk about with proportions, and I know this video has been going on for a really long time, but I'm just trying to be a bit thorough. What if you want to determine the sample size needed for a certain margin of error? So how are you going to do that? Well, you use the formula equation for margin of error. We know margin of error is basically just z star times the square root of p hat times 1 minus p hat over n. So this is the margin of error. We know this from the formula that we got for the confidence interval. Okay, we know margin of error. That's what we want to limit it to. We know z star because we know the confidence interval. We don't know n, and that's what we want to find. Do we know p hat though? You might think we do, but we actually don't in most circumstances because we didn't do the study yet. We want to determine the sample size needed for a successful study, so we didn't really do it yet. So we don't know these two. So how are we going to have two variables in this one equation? There's two cases. One, they provide a p hat. They say in a previous study, 90% of people said this. It's probably not going to be 90, but there's a second case. If they don't say anything, then you're going to assume it to be 0.5. Why? Because if it's 0.5, that's going to be the maximum possible value for this. If it's 0.5, then it'll be 0.5 times 0.5, which is a total of 0.25, which is the maximum possible product for p hat times 1 minus p hat. So that's going to be the worst possible scenario. So you want to be prepared for that, which is why you use a p hat of 0.5. So let's do a quick example of that. This is the same exact problem we did, but part B of that, I misspoke earlier. I said part A was the first part and part B was the 45%, but that was all part of part A. Usually it's going to be split into two, but in that case, it was just part A. And here, part B, it's asking what is a smallest sample size that can be used to guarantee that the margin of error will be less than or equal to 0.02. And this is a similar study. So we can use, the reason why we're using p hat of 0.5 in this case, you might be thinking, oh, well, we know that a similar study had 978 out of 23450. We can just use that. No, we cannot, because that was in the United States and this is in Canada. So they're completely different populations. So this is not a similar study in the same population. It's a similar study in a different population. So you have to use 0.5. Also, it says guarantee, and the only way you can guarantee is by using the worst possible scenario, which is 0.5. Okay, so whenever you have this kind of problem, you want to always do the algebra first. Margin of error has to be less than or equal to, or okay. So it's going to be a margin of error that's greater than or equal to z star times the square root of p hat times 1 minus p hat over n. You might be wondering, well, this is less than or equal to. Why are we doing greater than or equal to? Well, this ME is basically going to be 0.02. That is the value we want. And this is going to be the calculated ME. So this ME is less than or equal to 0.02. So let's do the algebra. First, we divide by z star. We have ME over z star is equal to square root of p hat times 1 minus p hat over n. Square both sides. You have p hat times 1 minus p hat over n is, this should be greater than or equal to. This is less than or equal to because we're looking at this side now. Is less than or equal to ME over z star squared. Now, one way to do this is multiply this side by n, divide by this other value. So I'm not really showing you the detailed algebra of this, but basically n has to be greater than or equal to p hat times 1 minus p hat over and ME over z star squared. That's going to be your formula. And now we can plug in values. So I'm going to clear all this. We know n has to be greater than or equal to, it's p hat, which is 0.5, times 1 minus p hat, which is also 0.5, over ME, which is 0.02, over n, over the confidence, over z star, basically. So you can go back. If you remember, you can use the previous value we found, but you can go back to distributions, go to inverse normal, and you want an area of 0.995 like last time, and you're going to get 2.576. So that's squared. So now you just plug it into your calculator. 0.5 times 0.5 is going to be 0.25. Now that divided by, and now don't forget the parentheses. You do 0.02 divided by 2.576 and all that squared. That should be in the denominator. So you have a total of 4147.36. That seems like a lot, but it is a pretty small standard margin of error. So the small sample size would be 4148 because it has to be greater than that. It can't be 4147 even though it rounds to 4147. Yeah. So that's an example problem of that. And now our last section, means. I'm going to go through this a bit quicker. The first part, no, because we have to introduce a new concept, but the next part, yes, because we just went over it for proportions. So the condition for means. So the conditions for means are going to be the same, but it's a bit different. Random condition, we know. 10% condition, we know. The large constant normal condition. For means, the fact is that either the population is normal, we're given that, or the basically the n, the sample size, has to be greater than or equal to 30. If that's the failsafe. If that's true, then we're done. If that's not true, we have to look at a graph of the data, and if there are any outliers or skewness, if there are any major outliers or skewness, then we have to say, okay, this isn't met. But if it's mostly pretty close together, then you can say, okay, it's pretty normal. Now we talk about the formula for confidence intervals of means. We have x bar, this time instead of p hat, plus or minus the critical value times the standard deviation. And this standard deviation is going to be the sigma over n. And this standard deviation is going to be sigma over root n. Now, what's the critical value here? This time we're going to have to use something called T star instead of Z star, and I'll explain why in a bit. We have a similar problem here. We don't know the population standard deviation, so we're going to have to estimate using the sample standard deviation, which is not very accurate, so we have yet another estimate. Okay, standard error, same thing as with proportions, except it's just going to be Sx over root n. It's also called the standard area of the mean because we're talking about means right now. And critical value T star is going to be the critical value that we're going to use. How do we know T star? So we're going to use something called the T distribution. And the T distribution is basically similar to a normal distribution, except it's a bit different. So I'll show you here. If you wanted a normal Z value from a normal distribution, it's going to look something like this. You have a normal distribution like this. A T distribution, though, is going to be like that. It's going to have more stuff at the edges. So that's the difference between them. And it depends on something called the degrees of freedom. The degrees of freedom is just going to be df. We talked about this a bit before, and it's going to be equal to n minus 1. The sample size minus 1. Here's a diagram showing you different types of graphs with different degrees of freedom. So the more degrees of freedom you have, the closer it is to being normal. So the purple graph is normal, standard normal, and the blue graph is 9 degrees of freedom, which means a sample size of 10. And the red dotted graph is 2 degrees of freedom, meaning a sample size of 3. So as you can see, for the one with less degrees of freedom, there's more area up here. It's bigger over here, so there's more area. And that's the difference. The closer, you're closer to the normal distribution if you have more degrees of freedom. And finally, there's the one sample T interval for population mean. And again, you should be able to do this on your calculator if you want, or you can standard deviation. So I'll show you an example a bit later. This is how you're supposed to write it. Basically the same thing. We're just replacing P with mu. And it's a T interval, not a Z interval. Same conditions. except there's one additional thing. The normal condition is a bit different. You do similar calculations and you interpret the confidence interval. Okay, let's move on to our example. Here we have a mean weight of 11.3921 grams of Oreo cookies and a standard deviation of 0.0817. The sample is 36 cookies. It's a random sample. Okay. Part A is asking us to construct a 95% confidence interval. Part B says the stated serving size is 3 cookies, 34 grams. So 3 cookies are 34 grams. And we're asked if the average weight of an actual Oreo is less than advertised. Okay. Let's write our answer. So we want to estimate mu, the mean weight of Oreo cookies. If conditions are met, we will construct a 95% one sample t interval for mu. Random condition we know is a simple random. We know is a random sample. It said so in the text. The next condition is the 10% condition. It said it was 36 Oreos, so times 10, 360. There are definitely at least 360 Oreos in the entire world. And large counts, well, 36 is greater than or equal to 30. So no further questions. We don't have to examine the box plot to see if there are any outliers or skewness. It already meets the large counts condition. Now we do the actual calculations. So that involves writing down some stuff. So we know that X bar is, as you can see from the question, 11.3921, and standard deviation is 0.0817. So since we're going to be moving to a different slide, you should probably make note of that. So to do the calculations, what you do is you start off by writing X bar is 11.3921. You know Sx is equal to 0.0817. And you know degrees of freedom is going to be 35. So this is going to be 36 minus 1. And now, how do you find T star given this? So I didn't talk about this before. I was going to introduce it in this example. So what you could do is you can go to where you would find inverse norm, and there's something called inverse T that you can use. So you give the area, which is 0.975. Again, this time we have a 95%, so you have to add that a little bit extra. So it's going to be 5% divided by 2, which is 2.5. So it's going to be 97.5%. Degrees of freedom, we know is 35. And we get a T star of approximately 2.0330. Now, the actual calculations you can show is going to be X bar plus or minus T star times the square root of, sorry, that was for proportions. For this one, it's going to be Sx over root n. Yeah. So X bar we know is 11.3921 plus or minus T star is 2.030 times Sx 0.0817 over root n we know is 36. Pretty nice number. So now you can plug it in. So if you go to where you found one prob z interval, you find t interval, just t interval. You use stats. You plug in 11.3921 as your x value, 0.0817 as your standard deviation of the sample, and n is 36. We want a C level of 0.95. And you're going to get from 11.3645 or 44 or 45, depending on how you round, to 11.4197. So that's going to be your interval. We did the do part and now the conclude. I'm going to clear the drawing so we have space. And yeah, from 11.3645, we're 95%. Sorry, it should be 95%. And now we have our conclude. So we are 95% confident that the interval from 11.3645 to 11.4197 captures the true mean weight of an Oreo cookie. And now we answer the other question that said, we know that 3 cookies is 34 grams. So if 3 cookies is 34 grams, then how much is 1 cookie? So you do 34 divided by 3, and you're going to get approximately 11.333 grams per cookie. Well, if you notice, 11.333 is actually less than all the values in this interval. So you might be compelled to think, well, it provides significant evidence or convincing evidence that the mean weight of an Oreo is actually less than advertised. But if you look at it, it's actually going to be more than advertised. This is the true weight, and this is advertised. So every single value in here is going to be greater than the advertised value. So it's actually the advertised value is actually underestimating the actual value. So there is no significant evidence, or there's no convincing evidence that the advertised value is greater than the actual value, or the actual value is less than the advertised value. So how we would write that is, as you might imagine, all values in the interval are greater than 11.333, so the evidence does not support this claim. And you can actually write out the claim if you want to. Okay, final thing, how to determine the sample size for means. Again, we use the equation for margin of error. This time it's going to be the margin of error is equal to t star times the standard deviation over root n. So just use that formula. This time you don't need a p hat to estimate. You're usually going to be given the standard deviation of a previous sample. And so there's no like, if it's not given, use this instead. No, you just use what you're given. So example, here we have 99% confidence interval, a margin of error of at most 2 texts, and standard deviation of 9. So how are we going to do this? Well, we know that margin of error is going to be greater than or equal to the t star times the standard deviation over root n. That means that margin of error over t star is greater than or equal to the standard deviation over root n. And now you divide by standard deviation, and you're going to get margin of error over t star times standard deviation is greater than or equal to 1 over root n. Reciprocals, you have root n is actually greater than, since it's reciprocals, you're switching it, is greater than t star times sx over the margin of error, and now you square both sides. So n is greater than or equal to t star times sx over me squared. And now you plug in values. You can find t star using inverse t. So that's going to give you an area. So since it's a 99% confidence interval, you know that it's going to be an area of 0.995. And then you plug in the degrees of freedom. That's when you realize we don't know the degrees of freedom. The problem is that we don't know the degrees of freedom because we don't know n. So instead, scrap all this, you're going to use z star instead of n star. So in this case, you would use z star. This is the only example of using z star with means. That's the reason is because you know that it's an estimate. The standard deviation divided by the margin of error, which is 2 squared, and you're gonna get an answer. So you can use your calculator for this. 2.576 times 9 divided by 2, and then you square that, and you're gonna get at least 134.374, which means it's gonna be 135 people. That's your answer. So this entire problem was just trying to show you that this is how you find the standard, the sample size that you need. And another purpose of this was to show you that you use z star instead of t star. So I started out with t star because that's what we're supposed to. And then once you realize that you can't find degrees of freedom, use Z star instead. Now that you know this, you just use Z star in general. But yeah, it was just a teachable mode. So that's actually it for this entire video. I know it was a really long video, but it covers most of the basic information we need to know for this unit. I went into a lot of examples in depth. So um, hopefully you prepared for the test, and I'll see you next time. Bye.